Hello all, welcome to this sixth session on structural analysis tutorial. Today we will discuss, I will give a brief recap of week 6 lectures. I hope you must have gone through week 6 lectures. And the problems related to ILD we will solve after discussing about the week 6 lectures in short. So, coming to ILD. First of all, can anyone tell what is the need of ILD? Means why do we need ILD?
Sir, to determine any particular point, the stress invariants like shear force and bending moment, to know at any particular point. That's why we draw
stress invariant. What do you mean by invariant?
shear force and bending internal forces.
Those are internal forces, not invariants.
Sorry, sir. Sorry.
Yeah. Those are, I must have written here. Those are stress functions, not stress invariants. Okay.
Okay, sir. Okay.
Yeah. So, when we discuss about ILD, ILD is basically related to moving loads.
Moving loads.
Have you ever heard we are drawing ILD for static loads? Or do you have any idea if ILD can be drawn for static load or not?
No.
Why no?
Moving loads.
We can draw bending moment diagram, shear force diagram, so we can draw influence line diagram also.
Yes.
So we will discuss this in detail in subsequent slides. So first let us read out what is the need of ILD. ILD is used to analyze the structure if load changes its position. Changes its position means the load are moving in nature or not static. Over the span length. Suppose, let us take a simply supported beam. This is hinge support and this is roller support. Let us see. And a unit load which is placed at a distance x. That x and that x varies within 0 to L, where L is the length of this beam. Now, at t equal to, suppose T naught, the load is at a distance x meter from this left hinge support. Now, after some time, when you observe this 1 unit load, let us say at t equal to T1, where T1 is greater than T naught, this 1 unit load has shifted here. Now, this is the new position of this unit load at T equal to T1. So for T equal to T naught, there will be some reactions here. Let this point be A, this point be B. The reactions will be RA and RB. Reactions are RA and RB. Now, when we are seeing that at some time T equal to T1, the reactions, let us say RA prime, RB prime. So those RA, my question is if RA will be equal to RA prime or not.
No, sir.
Yeah, no. So these reactions, which is a stress function, is not same. RA is not equal to RA prime after some time T1, which is greater than T0. So if load is here, there will be some reaction. After some time, load is shifted somewhere to the right, the reaction will be somewhat different. After some time, this load is again shifted somewhat right. This reaction will again vary. And this variation, when we'll plot in the form of graph or graphical representation, that will be termed as ILD. Till this point, it is clear or not?
Yes, sir.
Yeah. So this is for reaction, which is a stress function. The same thing can be done for shear force, bending moment, axial forces also. And these internal forces are also subjected or are also dependent on the external loading. As we know, that is the main reason we are drawing shear force and bending moment diagram. But shear force and bending moment diagram are for static load. Suppose this is a beam and you have a point load in the midspan and this is static. So you calculated all those reaction forces. Suppose, let us say, case 1, static case. This is a simply supported beam and one point load P is at midspan. So when you will draw the shear force diagram, it will be like this. And the bending moment diagram will somewhat come out like this. And this load is static. At T equal to 0 also the load was at midspan. At T equal to infinity also, where infinity is greater than 0, the load is at the same place without any further disturbance, as if it is behaving as a static load or dead load, what we call the self weight of the structure. It is not moving. So for that external load P, we are drawing shear force and bending moment diagram, and those are constant for static loads. But if the load is moving, this shear force and bending moment diagram also will change, because the reaction forces here and here will change with movement of this P. So due to which the shear force and bending moment will also come as a function of x, where x is the distance. It can be taken from any point as per your reference, means you have to fix a reference, and from that reference you have to calculate all those variations. Means like here I have taken x. So from left support I am taking that at x distance, at t equal to t naught, my load P, my load, that is unit load, is placed at x distance from left support, but it is varying. For this x, if this x is fixed, your bending moment and shear force diagram are fixed. But if this x is varying, this bending moment, shear force, axial force, reactions, everything will vary. And everything are related to each other, as we know in previous weeks. So when you go and plot those functions, you will get this shear force as a function of x, bending moment also as a function of x, axial force also as a function of x, and these reactions will also be obtained as a function of x. So when you plot, suppose you have n values for x, you will get output for also y output. This will be also you will get for n values. So when you will go and plot for y and x, you will get some curves. That curve is representing ILD for the given stress function. And that, suppose this point or this point, what it will represent? This point, suppose we are drawing for reaction, and this is some arbitrary curve I am doing. Suppose RA, and this is also RA. This is also RA. So the complete ILD, when you are drawing for RA, each and every ordinate represents reaction or that stress function actually. Means at any point, this point is also represent RA. If you are drawing the ILD for RA, this function is also representing RA. If you are drawing ILD for RA, this function also represents RA. So the complete graph represents RA. So many RAs are there. Why so many RA are coming, or so many for a given stress function? For a single stress function, so many points are coming. Can anyone tell? Because so many RA are coming, because if this we are taking as RA reaction, RA is also varying due to variation in this external unit load 1. So with variation of this unit load, this RA is changing. So these different points of RA represents a different location of external load. What is the RA value there? So throughout the span, when you will draw the ILD for RA, this will be total length, and this variation represents at x equal to 0, your RA value was this. At x equal to suppose L by 5, the RA value is this. At x equal to L by 4, the RA value is this, and at x equal to L, your RA value is this. So when you join all those points, you will get ILD for that stress function, which varies with external load variation over the span. So this statement states that. So coming to what is influence line diagram. So I have already described what is influence line diagram. Now let us read the statement, what they are saying. It is a graphical representation. As I have said, we can plot it. So we can graphically represent it. What that graphical representation suggests? It suggests or it signifies the variation of shear forces, bending moment, reactions, axial forces, or in general stress functions. Due to this point, different positions of moving load over the entire span. So, to summarize, if the load is static, we won't get ILD. When the load is varying, your stress function, that is shear force, bending moment, reaction, axial force, etc., will vary. That variation, when you plot with respect to the variation of the external load, which indirectly will be a function of x, all those stress functions will be a function of x. When that you will plot, that represents, that graphical plot represents influence line diagram for that stress function. So till this point, it is clear or not?
Yes, sir.
Yeah. So this is most important because, and this is also called as qualitative analysis. So Muller-Breslau principle was given by Breslau and Muller. It states that influence line diagram, if you want to draw for any stress function, that may be reaction, that may be shear force, etc., is the deflected shape of the structure after removing the stress function from the structure and applying a unit displacement, that might be rotation or deflection, in the positive sense. Suppose the simplest structure I am taking again. This is simply supported beam. Now, suppose this is point A, this is point B. So we have to draw ILD for RA. RA means this reaction at A. So according to this statement, they are telling ILD of any stress function. For our case, for now, it is RA. So ILD for RA will be the deflected shape of the structure after removing that stress function. After removing that stress function. So I want to remove this RA. So how this support will change? Now, this support is restraining translational movement along both vertically and horizontally. Now, I don't know about horizontal, but this vertical movement I want to allow for the given structure. So, if we will modify the support according to the need, that releasing RA, the support will become like this. And the complete structure will become like this. So this point is A, this point is B. So now, see, this is figure 1, this is figure 2. Now, we have removed the stress function, that is RA. Now, this RA, there is no restraining along vertical or upward movement. It can move upward directly. Now we have removed the stress function from the structure, and now this part is the second. After you modified by removing your stress function, you have to apply a unit displacement, delta equal to 1 or theta equal to 1. That will depend upon the problem in the positive sense. Now, tell me, this RA we have removed. Now, this can move easily. So, you take this joint A above by how much distance? This should be 1 unit. That is 1 unit displacement. Now, you join. This is a straight line. I am drawing it again here. So this is ILD for RA. So this is the complete statement given by Muller-Breslau principle after doing so much of experiments. And this is related to Bette's law. Bette's law, or you can tell Maxwell reciprocal theorem. There is a big derivation for this. I am not going through because it has been given in detail in the lecture series. So now let us draw ILD for RB. Someone please unmute yourself and speak how ILD for RB can be drawn for same beam, same simply supported beam.
The unit displacement shall be given at point B.
Okay. How this support will change?
The support will move upward.
No. Support, how can support move upward?
Sorry, the point.
Yeah. This is a roller.
Yes, sir.
Think means visualize it. Don't mug up, visualize it. Roller. How many constraint roller gives? First, tell me that.
1.
In which direction?
In vertical direction.
Vertical direction. Any other constraint this roller provides?
No, sir.
It allows movement. It allows this horizontal displacement. The only thing it does not allow is this. That's why we write reaction at B. So, if this is the only thing it is means restraining, then how this support will be modified such that we can apply 1 unit without hampering, means by removing RP and without hampering any other restraint of the total structure. How to modify this B joint such that we can draw the ILD. Now tell me, A is now hinge.
Then we can apply any unit rotation.
Why to apply unit rotation?
Because it shall, as you said, it shall allow rotation.
No, then it also allows HB. But what is our aim? To determine ILD for reaction RB, that is vertical reaction RB. What Muller-Breslau principle states, read one more time. It states that the ILD for any stress function, as you said, suppose we have to make ILD for this reaction RB, then we have to remove this reaction and give 1 unit displacement. That's it. You are getting right?
Yes, sir.
Speak where you are getting stuck. Let me know, otherwise how I will make you clarify.
Yes, sir, I know.
So like this was hinge support. Hinge is providing this, suppose AY, this is joint A, this is AY, this is AX. Now we wanted to draw the ILD for AY. So I have modified this support like this, such that AX remain intact, but AY is removed. That stress function is removed. After removing, you can give 1 unit displacement. But with this RA, if that RA will be there, can you means move that support up, keeping RA intact? No. So you have to modify this joint such that that stress function is released. After that is released, you just lift it by 1 unit. That will be the ILD for that stress function. So here you see, this is roller. This HB is not here now. No HB, no horizontal reaction is there. No movement is there. The only reaction is RB. So I have to remove RB. So remove completely. There won't be any, the support will be modified like this. The roller is providing only one support. I have to remove the roller directly and just give 1 unit displacement and join it to this part. This will be ILD for RB. Suppose for this, I want ILD at midpoint, make it third point, ILD for simply supported beam at midspan. Tell me how we'll draw at this point. See, according to statement, first is you have to remove that stress function. That is step 1. The second step is after removal, you just give a unit displacement such that it does not affect the compatibility of the structure. Give unit displacement such that the compatibility of the structure as a whole is maintained. Otherwise, the ILD will be wrong. Now tell me, simply supported beam has, we have to draw for shear force at C or at midspan. Tell me. Biranji, tell me. If you are not getting asked, why are you sighing out?
Okay, sir. You tell.
Now, we have to draw ILD for shear force. So at this section, we have to release the shear force. So how we can modify this point, that is midspan, such that we can apply unit displacement at that point. So we can directly provide a shear release. Shear release will remove the shear force at that point C. This is support. This is hinge support. This is roller. Now, from first lesson, I have said shear force at a section. Let me add one more slide. This was the beam. We are cutting the beam from here. Suppose section A, and after cutting, we are getting two parts. Let us say this is part 1, this is part 2. So, when we are showing like this, left side upward and right side downward, for this is for the element. This is elemental view. And this is at that section, cut section. A, we are showing shear force like this, and this shear force is the positive sign convention we will follow. Now, so here, so this was the midspan C, this is A, this is B. We have to release the shear force, so we have dissected the beam into two parts, and we have given a shear release. This joint is called as shear release. Now, this C point, at this C point, we have given this shear release. So, this is acting like a cut section. At this section, our shear force sign convention for positive shear force case will be like this. Left side downward, right side upward will be positive. So just pull it down and give the right side a upward lift. So when you do that, you will get something like this. This is negative, this is positive. And this complete lift will be unit. This is the ILD for shear. You got it, right?
Yes, sir.
Yeah. So the last part, please tell me how to draw for bending moment. It suppose not at mid span, but somewhere other at any other point apart from mid span. Let this point be E. I am drawing the ILD. The ILD will somewhat be like this. Now tell me what joint or how we will modify this point E such that our stress function is released. Means bending moment at point E is 0. Tell me what joint to apply. Like here, to release shear force, we have applied shear release. So to release bending moment at E, what joint we need to apply?
Moment release or internal hinge.
Yeah. So when you will apply a bending release here and give unit rotation 1 and 1, you will get this is the ILD for bending moment. This is positive. You got now how to play with supports so that our stress function is first released. That is our first step. After releasing the stress function, apply a unit lift. Means that may be in form of rotation. Like for this, we have used rotation, or like in form of unit lift. Like we have used it here. The same thing we have used here also for reaction. Clear till now?
Yes, sir. Yes.
Now let us solve some problems. Now, in this question, they are asking to choose the correct influence line diagram for shear force at point C of the following simply supported beam. And C point is here somewhere. Now, how we can do that? Just dissect the beam at C, apply. We have to release shear force at point C. So dissect it, apply shear release, and draw the ILD for shear force at section C or point C. Now let us do that. When you will at this point C, when you will put shear release will be like this. And recent in the previous slide only, I said at a section, left side downward and right side upward is the positive sign convention for shear force. So we have to put left part downward. So this left you pull down and this right pull it up, such that this total lift should be unit. So now this is C. This total lift will be unit. This will be unit. So for this to be unit, what you can do? And one more thing, for statically determinate structure, when you are doing shear force, ILD for shear force, this line and this line will be parallel, such that if you are writing alpha here and this alpha will be same. So now what you can write? Alpha will be, means for civil engineering structure, we know the displacement is very small and this alpha, when we are writing, that rotation is also very small because unit displacement is also very small. So tan alpha, you can write it as alpha. So alpha will be equal to, let us say this is x and this is y, and from question, this is 14 meter and this is 6 meter. So alpha we can write for first one, this will be x by 6. Similarly, when you take the bottom triangle, it will be y by 14. But alpha is same. So you can equate x by 6 will be equal to y by 14. And we know we are providing unit displacement. So x plus y will be equal to 1. So just simplify it. X equal to 1 minus y you can write. So 1 minus y by 6 equal to y by 14. So 14 minus 14y equal to 6y. So what you can write here? 20y equal to 14. Y equal to 14 by 20. 0.7. So y we got at 0.7. So x will be 1 minus 0.7. That is 0. So which option is correct? I think option B. Yeah. So is there any doubt in this question? Okay.
Sir, how I got x equal x by 6 y equal to 14?
Sorry, can you speak out again?
How we got x by 6 and y equal to 14? How we got it?
Tan alpha equal to alpha for small displacements. This step, are you comfortable with or not? Why we are writing tan alpha equal to alpha?
Yes, sir, comfortable.
Yeah.
Tan alpha is not equal to alpha.
So tan alpha will be from trigonometry. What you know, tan alpha will be height by base.
Yes, base is right.
Correct.
Height by base. Yes.
So for this upper triangle, when you will write tan alpha, it will be x by 6, right?
Yes, sir.
Yeah. So tan alpha equal to alpha, that is our assumption. Means for
Yes.
not assumption, means it is from geometry only. Tan alpha will be equal to alpha for small displacement or small
Okay.
rotations.
Okay.
So it will be x by 6. Similarly, for when you are taking lower triangle,
What?
what will be tan alpha or alpha? It will be y by 14.
Yes, y by 14, yes.
Yeah. And these alpha are equal.
Yes.
So you are getting one equation, let us say equation 3 from this. Now, from Muller-Breslau principle, what I have said, in step 1, you have to remove that stress function for which you need to draw the ILD.
Yes.
Second, you have to give unit lift.
Okay. Okay.
So delta equal to 1.
Yes, delta is 1.
Yeah. So if delta equal to 1, then this plus this should be equal to 1.
This and this should be equal to yes.
Yeah. So equation 4, you can write x plus y equal to 1.
Yes. Equation number 4.
Now you substitute, means I have done it in this way. You can do it other way around. You write this equation as a function of y. So x equal to 1 minus y and substitute it here. You will get the value of y.
Yes. Okay.
Once y is done, you know x will be 1 minus y. So 1
Yes.
minus 0.7 will be 0.3. So
Yes.
you got both the ordinates. So your ILD for shear force at joint C is done and dusted.
Okay.
Now tell me if there is any problem anyone is facing. Apart from the problem I have discussed now.
Sir, how we got 1 minus point, sir? 1. How you got 1 here?
Where this one? Or which one? One means which one you are telling?
Yes, yes, so yeah.
This one, right?
Yes, this
Yeah.
1 minus point 7. How we got this value? Minus 0.7 before that.
This 1 minus 0.7, how we
Yes.
got?
Yes.
We are giving it a unit displacement, right?
Okay. Okay.
That is the major thing, major chunk of Muller-Breslau principle.
Okay, I got it.
Yeah. So you can also do it by writing the equation. Let us do. If you are not comfortable, I am doing it in that way also. Let us see if that is coming or not. From Muller-Breslau principle, we got in that fashion. Let us prove it also. Observe carefully. Now, this is point A, this is point B, this is point C. Now, this is unit load I am placing at a distance x from left support. So, now from equations of static equilibrium, we can find this RA and RB because this is a statically determinate structure. Now let us do summation of moment about point B of I equal to 0. So when you will write, you will get RA into, let us say, this is at a, C is at a distance of Z and total length is L prime. Now, RA into L prime minus 1 and I am taking clockwise to be positive. Clockwise movement to be positive. So RA is producing a clockwise movement about this point B and 1 into what will be the lever arm? It will be L prime minus X. Because lever arm for this one will be from this point till point B. And that will be equal to 0. So from here, we will get RA equal to L prime minus X by L prime. Simplify it. This will be this. Similarly, not similarly, you can directly write RA plus RB will be equal to 1 by doing summation of Fy equal to 0. And vertically upward, I am taking as positive. So RB will be 1 minus RA and RA we got as, I am directly substituting 1 minus X by L prime. So when you will simplify this, you will get X by L prime. Correct? Till this point, is there any problem? No problem. Okay. Now, for shear force at C, now I am dissecting, cutting the beam at C. and drawing the free body diagram for left. So this is 1 minus x by L prime. This length is Z. Our unit load 1 is at x. Now tell me the shear force here, if we want to show it in positive fashion, then will the arrow be upward or downward? Tell me, I have discussed it now only.
The direction shall be downward.
Yeah, downward. So let us tell it VC. Now we can write VC will be equal to, like you can again do summation of Fy equal to 0 and positive upward. I am directly writing 1 minus x by L prime minus 1. So we are getting minus x by L prime. And here the variation of x for this case will vary till Z. And can anyone tell if it will be less than equal to Z or only strictly less than Z? It will be strictly less than Z, because at a section shear force is not defined. Slightly less than that or slightly more than that, in that periphery shear force is defined. So it will be strictly less than Z. So this is first case. Second case, it will come like this. When your 1 unit load in this X surpassed this point C and moved rightward of C. Now it is like this. This is 1 minus x by L prime. And your 1 unit load, if this is point C and this is also point C. And this 1 unit load is at a distance x, and this length is Z. Now, again write VC. Here, what you will get VC? This VC will be equal to this upward force 1 minus x by L prime. And here, x will vary from, x will vary from Z to L prime. Now, this is 0 point, this is L prime. Now, C is at a distance of Z. So, when you will put x equal to 0, you are getting ILD for shear force at this origin point. It will be 0. When you are putting, you cannot put Z directly, means at Z, exactly at Z shear force is not defined. Just left or just right, means it's like Z tending towards that point. So just put Z, it will be minus Z by L prime at that, if this is C point, just to the left of C. This is minus Z by L prime. Now come to this side. When this unit load cross that point C, which is at a distance of Z from left support. Now put here x equal to L prime. When you will put, it will be 1 minus L prime by L prime will be 1, which will ultimately give you 0 here. Now, when you will put Z, and again in this equation, it will be 1 minus Z by L prime. This ordinate will be 1 minus Z by L prime. And why I have drawn it linear? Because we can see x is linear. That VC, which is a function of x, is linear. The second case also, VC, which is a function of x, is linear. Now just see, at this point, when you add, like in the previous case, we have taken it as y and x, and we are telling directly that 1 unit displacement. So you add it here. This is 1 minus Z by L prime. Just take the mod, because algebraic addition should be done. One is in negative side, one is in positive side. And this will be minus Z by L prime mod. So just add it. This will get cancelled out and you are ultimately left with 1. What we got? This total is 1 unit displacement. You got this point, right? This is the complete proof how that delta equal to 1 is coming here. Who was asking the question? Please tell me if you got the concept or not. Okay, everyone got clarity, right?
Yes, sir. Yes, sir.
So I am moving forward to the next question. Now here, in the same question above, they are telling we need to determine the maximum shear force at point C in the beam shown in figure 1, that same beam. I am drawing it here again for clarity. This was point C. This was 14 meter. This was 6 meter. If a uniformly distributed load of 10 kilonewton meter of length 5 meter moves on the beam from right to left, means your loading is something like this, a UDL having length means W of 10 kilonewton per meter, length of 5 meter. It will move from right to left and cross this beam. We have to determine at certain time t, when this load is placed somewhere in the beam such that the beam will give the maximum shear force at point C. Means at point C, by placing this UDL, we have to maximize the shear force at point C. Means the thing is, we have to place this load in such a way that we will get shear force at C to be maximum. Now, we have already drawn the ILD for shear force. It was like this. this was 0.7, this was 0.3. This is 14 meter, we know, and this is 6 meter. So, and this is negative, this is positive. The maximum shear force at point C we need to determine. That maximum means mod value, means we are requiring the magnitude only, not positive negative, means sign is not a matter of fact here. Now, we have to place this 10 kilonewton per meter such that we will get maximum shear force at point C. So what can be done? Where we can place? We can place it here. I am seeing this ordinate 0.7 is more as compared to this ordinate point. So if we will place the tail of this UDL at C such that it occupies 5 meter to the left of C, then we will get the maximum shear force. Let it be negative, but magnitude wise it will be maximum. So this area will provide us the maximum shear force at that point C. So this is 5 meter C. For 14 meter horizontal, there is a lift of 0.7 meter. So, and this is 14 meters and this is 5 meters. So this will be 9 meter. So point for 9 meter horizontal distance, this vertical ordinate, you can directly calculate from similar triangle. So you take the big triangle and you take this small triangle too. We can write 0.7 by 14 will be equal to, suppose this is x by 9. So we are getting x equal to 0.7 by 14 into 9. So it will be 0.45. So this ordinate is 0.45. Now we can write shear force max at C will be equal to, just calculate the area. It is a trapezium. So half into sum of parallel sides. So x means 0.45 plus 0.7 into height. Height is this 5 meter into what was the magnitude? 10 kilonewton. So into 10. So what we are getting? Can anyone tell what is the value we are getting?
28.75.
28.75
0.75.
kilometers. So option A. Clear, right? This question is clear.
Yes, sir.
Next. Here also again we have to select the correct influence line diagram for shear force at point D. Point D is this point of the following beam. So first, let us do it with equations of equilibrium and let us check if the answer is matching with Muller-Breslau principle or not. Means let us do by case 1. It is not case 1, but we can by equations of equilibrium. Now I am drawing the free body diagram. Now I am placing, this is point D. So I am placing this 1 unit load which is moving. Now it is at a distance of x meter from this fixed support A. So when we are drawing the free body diagram, we can directly draw. This will be AY reaction vertically upward. This is MA movement. This is point D. And this is bending release or internal hinge. Here, let us say this is CY. This will be CY. There is bending release, so bending moment will be 0. I am not showing that. This will be BY. Now, I am keeping our unit load 1 here, which is at a distance x. And x, now case 1, x is less than equal to 0 and less than equal to 8 meter. Now within this domain only, this 1 unit load is moving. Now let us calculate all those reaction forces. When this 1 unit load is moving between A point and D point, these reaction forces CY and BY, what will be the magnitude? It will be, there is no vertical load here. So it will be 0 and 0 because the beam is not loaded. So there won't be any reaction. So CY is 0, BY is 0. If this CY is 0, this CY the same because shear force at a point just left and just right will be same. So CY is 0 here. Now, once that is done, what you can do for this left part, I am writing summation of movement about point C of I equal to 0 from left hand side. So what we will get? AY and clockwise I am taking positive. AY into this length is 12 meter. So into 12 plus MA minus 1 into 12 minus x equal to 0. Now, this is equation 1, sorry. This is equation 1. Similarly, again we can write summation of force along y direction equal to 0 and vertically upward I am writing it positive. So AY minus 1 will be equal to 0. There is no vertical reaction apart from these two. So AY we are getting 1 directly. Now, when we will substitute AY equal to 1 in this equation 1, what we will get? MA we will get, it will be 12 minus x by 12. So this is MA. We have done it correctly, right? AY into 12, 1
minus 12, sir. By 12 kaadu. It's not by 12, sir.
Sorry. Minus 2. Will be 12 minus x minus 12. So 12 will get cancelled out. We will get minus x. Now, so now we have to again, this is case 1 when this unit load is varying between this A point and D point. Now similarly for case 2, when our unit load will vary between 8 meter to 12 meter, means this span. I am not drawing the figure again because all those values will remain same. Cy will be equal to 0 again. Dy will be equal to 0 again from similar concept, because your unit load will be moving between D and C and there won't be any load in this span. So both Cy and By will be 0. So this will get transferred here. Again, this Cy will also be 0. Now, when this one unit is moving, this same x distance it will follow. So both all those things, Ay will remain 1 as it is, and Ma will be minus x. Now the third case, case 3, when your x, that your unit load is varying between this point beyond C onwards to point B. So it will be 12 meter to 20 meter. Now, this is your Ay, this is your Ma, this is your point D, this is Cy, this is Cy, this is By, and this here your one unit load, which is at a distance x from point A, from left support. Now, what you can write here, summation of, again apply equations of static equilibrium, summation of moment about point C of I equal to 0 from right hand side. Now, when you will do, you will get By, clockwise I am taking positive, so minus By into this length is 8 meter, minus By plus 1 into, what will be the lever arm? It will be x minus 12. That will be equal to 0. So from here, you will get By as x minus 12 by 8. So you can write x by 8 minus 3 by 2. Now, you do summation of forces about y direction, along y direction and upward positive equal to 0. So you will end up getting Cy plus By will be equal to 1. From here, Cy you will get 1 minus By. So 1 minus x by 8 minus 3 by 2. So it will be 2.5 minus 3 by 2 plus 1 is 5 by 2 minus x by 8. You just keep on checking if the calculations are correct or not. Otherwise, you will end up getting wrong results. Now, once By is done, Cy is done. If this Cy is done, this Cy will be same. Now come to this section. Now, Cy you got 2.5 minus x by 8. So here, for this part, this is for right span. Now summation of Fy equal to 0 if you do for left span, you will get Ay will be equal to Cy will be equal to 2.5 minus x by 8. So you got A1. Now check the left span. Ay is acting upward, Cy is acting downward, having the same magnitude. So they will try to rotate the structure clockwise. If our assumption of the direction is correct, I am assuming that our assumption is correct. So Ay and Cy will try to rotate the structure, left part only, clockwise. So to restrict that, MA should act in anti-clockwise manner. And that MA, what will be the magnitude? It will be 2.5 minus x by 8 force into the separation distance or the lever arm between them. This is 12 meter into 12. And this MA, we have shown it in this way. So if you want to keep this direction, so you have to add another negative sign. Because if Ay and Cy, as per our sign convention, if our directions are correct, they will try to rotate it clockwise. Try to rotate the beam in clockwise manner. And that MA is the only resisting force that will provide resistance to keep the beam intact and statically stable. So MA should act anti-clockwise, but we have shown it clockwise. So I am writing explicitly a minus sign for that. Or else, to make it easy, let us change the direction here only. This will be MA now. Now we got MA, AY, CY, BY for every, means we got all the reaction now. Now we can calculate for our stress function, which is shear force at point D. Now to determine shear force at point D, let me add one more slide. Now cut the section at T. I am cutting the section at D. And when our unit load 1 was moving between A and D, we got Ay as, what was the value? Ay as 1. And this was X. And X was varying from 0 to 800. And this is MA is minus X. Anything left? When we have dissected the beam from joint D or point D, shear force will come and our positive sign convention is downward for this section. So let us tell this is VD. Now tell me VD will be what? What will be VD? It will be 1 minus 1, 0. That means when our unit load, suppose this is A, this is point D, and our unit load is moving between this, then the shear force at point D is 0. Means ILD will be 0 for this span A and D. Now, when this is A, sorry, this we got 1, and this is D, and now this is D, this is C, this is C, and this is B. Now our unit load is moving between this D and C. And here the distance is X from left support. Now you need to again ascertain VD here when the unit load is passing between D and C. Now, and this will be -6. Now tell me VD will be 1 directly. That means your ILD between D and C will be constant and its magnitude will be 1. So we got when unit load is moving or traveling between A and D, your ILD is 0, which is constant for that span A and D. When your unit load is traveling between D and C, the ILD for that span D and C will be constant, but now the value has increased to 1. Third case. Now, this is A, this is D, this is D, E, this is C, and B. Now your unit load has shifted to the last span. And from here, the distance is same, X. Now tell me what is this reaction? This is 1 or some other value? Tell me, what will be this reaction? Means value of this reaction force. You have calculated only. Tell me, in this slide only I have written somewhere. Tell me, this value, AY is this, 2.5 minus X by 8. And the moment is 2.5 minus X by 8 into 12. Now, this VD will be directly equal to this reaction because both are acting, means VD is acting downward, AY is acting upward. So they will try to balance out each other such that summation of Fy equal to 0 in vertical direction. Now, we have done everything. Now we have to just accumulate all those information and draw the shear force diagram. Draw the ILD for shear force at point D. Now, I am drawing the ILD here. How was those? A, D, C, B. A, This is D. This was C. This was B. Now, when between A and D, when the unit load was moving, we got the shear force at D is 0, means when the unit load is moving between A and D, your all the ordinates between A and D will be 0. So draw between A and D, your all ordinates is 0. Now, when the unit load surpassed D and it is traveling between D and C, you got VD as 1. So just it will increase to 1. Now, when your VD here for third case, when between C and B your unit load is moving, you got VD as 2.5 minus x by 8. And this here, x is varying between this C point to B point, means 12 meter to 20 meter. So now tell me, when you will put x equal to 12 meter, what you will get? 12 by 8, 3 by 2, 1.5. So 2.5 minus 1.5 is 1. So it's 1. Here it is 0. So complete it is a rectangle till point C. Now, when you will put x equal to 20, it will be 0. And the power of x is 1. So linear variation between C and B. And this is positive, and this is the ILD for shear force at C. Got it, right? So option A. Now, let us check with Muller-Breslau principle if we are getting that or not. Now, check. We have to draw the ILD for shear force at this point D. So cut this point. Here shear release will come. I am not showing, I am directly bifurcating it into two parts. Can anyone tell, is this a statically determinate beam or statically indeterminate beam? Although in the next week we will start determinacy and indeterminacy and how to find out. But as per your knowledge, if you can say if it is indeterminate or determinate.
It's a determinate structure.
Determinate structure. And one thing you note it down, that for determinate structure, the ILD will always be linear. It cannot take curvilinear shape or higher order curves. So now here release we have inserted and we will now lift it. Now tell me, when we will give here for left part, when we will try to pull it downward, will it take a linear shape or will it bend? When this shear force we are acting, we are giving, will it take a linear shape like this or will it try to bend like this? Tell me, will it be a linear or will it be taking a curve shape?
It will take linear shape.
How come it will take linear shape?
Sir, your
No. First of all, it should take linear shape.
yeah.
For all the determinate structure, where is my picture? For all the determinate structure, it should be linear, and it is complete as a whole, it is determinate. So, according to Muller-Breslau principle, for determinate structure, the ILD should be linear. But when this is like a cantilever structure and you are applying a point load here, so when you will draw the elastic curve or deflected shape, it will try to bend in a non-linear fashion. So for this part, the ILD, the ordinates of ILD will be 0 from A to D.
Oh,
Now come to this part. When we will try to, if this is 0, then this upward lifting will take complete a 1 unit vertical uplift. So this will be 1 unit lift. So you lift it by 1 unit. Now you tell me, there is a internal hinge here and there is a roller to the rightward of internal hinge. So when you will try to lift from this point, the internal hinge will try to lift with this 1 unit lift at joint D. So now you have given 1 unit lift here. So the ILD will come like this. And this is a roller support. It won't lift or go anywhere in the vertical direction. Now join here. So your ILD comes to be same what we got from mechanics. Till this point, is it clear?
yes, sir. Yes, sir. Yes.
Now, for the same problem, we have to determine the maximum bending moment at that same point D, as shown in the previous problem, due to live load of 5 kilonewton meter. I am drawing the figure again so that you will get clarity. This is D. This was internal hinge. This is point A, B. This was 8 meter, 4 meter, 8 meter. Now, at this point, we need to determine the maximum bending moment using the concept of ILD. Now, we won't do using the concept of mechanics. We will directly plot from qualitative analysis, that is Muller-Breslau principle. We will directly plot the ILD and we will determine the maximum bending. Now, check. Here, you need to determine the maximum bending moment. So which type of support we need to incorporate at point D? Bending release? Correct?
Yes, sir.
Yeah. Incorporate bending release. Now, we have to give unit rotation. Now check. The left part, when I will do it separately, you put a rotation, it will take curve shape. But this is not acceptable for linear, elastic, and statically determinate beams. So this part here for ILD for bending moment for point D, all the ordinates between A and D will be 0. So the complete unit rotation will be taken by right part, that is D, C, and B. So when you will draw the ILD, here it is D, it will get rotate and rotation will be unity from here. This is D, this is C, this will be the ILD for bending moment at point D. So anyone having confusion, please let me know now. Why this AD portion everywhere, the ordinate of this ILD for this AD section is 0. Everyone got it right? Because it is a statically determinate beam. According to Muller-Breslau principle, if a beam or structure is statically determinate, then no part of the ILD will be non-linear, curvilinear, or higher order term. It will only take linear shape or constant shape. If not linear, then it will be 0 direct. So for AD section, it was 0 because when you will put unit rotation or some part of the rotation there, this AD portion will try to bend non-linearly, and non-linear portion for statically determinate and linear elastic structure, the ILD can't be non-linear. So put directly 0 there. Now this is the ILD or bending moment at D. Now check, this is 4 meter, this is 8 meter, and here theta is 1. So tan theta will be equal to theta because theta is very small, and if this is 1, tan theta will be height by base. So tan theta equal to theta will be h by b will be equal to c prime c by dc. That will be equal to 4 by 4, and theta is 1. Sorry. C prime c by 4 will be 1. So c prime c will be 4 meter. So this is 4 meter. Now we need to find the maximum bending moment at point D. For the live load of 5 kilonewton of span more than the length of the beam. If a 5 kilonewton per meter this here, its length L is greater than length of the beam, that is 8 plus 4 plus 8. So you place this load in such a fashion that this area is completely covered. Anyhow, if this is more than span length, so put the entire UDL over the span length such that it covers the entire span, and some portion will be out of the span. Let it be, because that is not of any use for us. So we have just superimposed the load completely over the span. Now the maximum, the maximum bending moment you can get directly. Calculate this area, multiply with this W, that is 10 kilonewton. Sorry. This is 5 kilonewton per meter. So let us calculate bending moment maximum at D will be equal to, what will be the area of triangle BCD?
Half into base into height. So ultimately it comes 24 and multiplied with 5.
So half into 4 into 8 plus 4. This is the area into 5 kilonewton per meter, that is superimposed load. So into 5. So this is coming out to be 24 into 5. So 240 by 2, 120 kilonewton meter. So option C. I hope this question is clear.
Yes, sir. Yes.
Now, this question is an interesting question. Here, we have to determine the ILD for different cases, and we have to check if those are correctly matched or not. Now, let us check it. Now, ILD for vertical reaction at B. If we have to determine ILD for vertical reaction at B from Muller-Breslau principle, what it states: remove that stress function, apply unit lift or unit rotation along the positive direction or positive sense. So when we will remove this RB, reaction at B, and apply a unit lift, this will try to take shape like this. And this will be 1. This will be ILD for vertical reaction at B. But what they have shown, they are showing this is unit lift, but it will go till point D. But there is a bending release, and bending release, when you will try to lift point B, there is no resistance against bending. So it will rotate from point C, but not from point D. It will rotate from point C, but not from point D. So this is wrong. And the correct ILD should be, I am drawing the correct ILD also here. It should be like this. And this should be unit. Now, ILD for vertical reaction at A. Remove RA and apply unit lift at joint A. So let us do like this. The joint condition will be modified like this. D will be remaining as it is. C is internal hinge. B will be C, B, D, A. and here you have to give unit lift. So joint A will move to A prime, and how it will take the shape. See, this D point can't go anywhere, and this C point does not have any bending resistance. So when you will try to lift it, this D point won't go anywhere, and your ILD will always be a linear shape function, because for statically determinate structure according to Muller-Breslau principle, it should be linear but not non-linear. So you can join like this. Now it will move forward till joint C like this. There won't be any bending resistance at C, so it will directly go downward. And from compatibility, this C point is a single point. So from B also, it will try to rotate like this. So ILD for RA will be this. But what they have shown till point B, it will vary linearly, and the slope will be constant. But this is also wrong. So B is also wrong. Now check third case. Third case, they are telling ILD for bending moment at D. Now see, I will draw for this case because this is confusing. You have to draw ILD for bending moment at this support D. So according to Muller-Breslau principle, you have to allow a bending release here. So once you are done with this bending release, I am drawing the figure here so that you get a visual clarity. It will be like this. And there is one more ruler. Okay. Now, hinge also. Now, we have removed our stress function by applying a bending release. Now, we will give rotation in positive sense, and this is the positive sense at a section for bending moment, that is sagging. Now check for left part. When you will try to rotate it, it will try to take a curved shape. This will try to take a curved shape, but this is not allowed. So ordinate for ILD for this part will be 0. There won't be any ordinate having a value for the ILD of bending moment at D for left part. Now check the right part. When you are giving 1 unit rotation, because here there won't be any rotation, so complete rotation will come to the right side. So it will try to rotate like this. Check. It's all the lines are linear, but I am unable to draw it linearly. So from line diagram, if we want to show, then the ILD will be something like this for bending moment at D. And here The entire rotation will be unit. So, and this should be negative, but they have shown it in the opposite way with a positive sign, so it is completely wrong. So anyhow, this is MCQ, so option D is correct. But let us check the shear force ILD for shear force at C. Now, here, when you will draw ILD for shear force at C, you have to insert what? Shear release such that your stress function, which is shear force at for the fourth case, is released. Now apply unit lift. Now check. For shear force, this part at a section, this part downward and this part upward is taken as positive sign convention. This is the sign convention we are taking. Now, when you will pull it downward, the left side will try to take the shape like this. Sorry. Is this linear or non-linear?
Linear, sir.
Non-linear. It will be non-linear.
Which part?
When you left part.
Yeah. DC part, right?
ADC part.
Yeah, AD will be non-linear, but I'm saying about the DC part.
Now, complete when you are, how to tell you? Do this. Suppose, see the screen. This is point C. Suppose this is point D, this is point A, and this is point C. When this D joint cannot move in upward direction, means vertically, it cannot move. So when you will try from point C, you are pulling it downward, and this is elastic. So here you will get a shape like this, such that compatibility is maintained. How you will check the compatibility at this point? Both, when you are checking this slope and this slope should be same, and that curve will extend till that point where you are pulling. So it will be a higher order curve, but not linear. So for this part A to C, the coordinates will be 0. Now this part is not coming downward, so entire lift will be in the top and upward. So now B, it is roller, and there is no bending restraint here. So when you are giving a 1 unit pull, 1 unit uplift, so it will just tend like this. So here you are giving unit uplift delta, it get uplifted there is no bending resistance at point B. So directly you join. So this is the ILD for shear force at C. Clear?
Yes, sir. Yes. Yes. Now I.
Means if you are thinking this part about this part, you can do in the same way I have done the previous problem for shear force. You just, because this will take time and unnecessarily it will elongate the class. So I am not doing it. Otherwise, we can do it. But as of now, I am not doing it. If you
No,
are
sir, no.
facing any problem, then mail me. I will send you the solution.
Okay, sir. Okay.
I am telling just put the unit load here between A and D. Write all the reaction forces. Shift the unit load to when it will move between D and C. Again, write all those reaction forces. Similarly, for this span B and C, shift the unit load, write all the equations. Now, you are interested in determining whatever stress function ILD you want to determine. Once you are done with all those things, at which section you want to determine the value, you go to that section, cut that section at that point, so the reaction for which you want, so the reaction means so the stress function for which you want to draw the ILD. Like in the previous case, for shear force, we have to draw shear force ILD at point D. So I have done it section by section, showing the shear force only, because there will be movement, but I haven't shown because that is not our concern for this case. There will be MD. I am not denying this fact, there will be MD. But for the case, we are least bothered about this movement. We are interested in VD. So calculate VD, shifting your unit load. Similarly, here you cut the section from C, apply VC, that is shear force at C, shift your unit load between AD, DC and CB, calculate all those RA, RD and all those forces. Then you see, when your between D and C, when your unit load is moving, you will get VC at 0. That will suggest that the elastic curve or between ADC, that when you are pulling it down, that will take a non-linear path, due to which the ILD won't accommodate the non-linear part for linear, elastic and statically determinate structure, so that all your points for that part is becoming 0 and you are ultimately left with BC region having a rectangular domain with a lift of 1 at point C. You got it, right? Yeah.
Yes, sir. Yes.
Now, let us check this question, what they are telling. You need to determine the maximum bending moment at D for the previous question only, due to moving load of 20 kilonewton of span more than length of the beam. So at D, ILD for bending moment at D will be like this. For left portion, all the ordinates of ILD will be 0 because it is taking a curvilinear shape. Between D and B, it will form a triangle shape. So our ILD will be like this. This is C D A B. It will take the shape like this. We have already drawn it. I am redoing because you have to calculate the area and all. Now, check. This theta was 1 because in this direction there won't be any rotation. Now, this length was 4 meter, 4 meter, 2 meter, 2 meter, 2 meter, 4 meter, 2 meter. Now, if this theta is 1, so directly you can write now this height will be 2 meter. Now, tell me the area. Area will be half into 2 into base 2 plus 2. So it is 4 into now 20 kilonewton per meter having a span length greater than the span of the beam. So directly superimpose throughout the beam means there might be a case it is increasing this side or this side, but we don't know. Just take the maximum length equal to the span length and put it above the beam end. And this is area, and what is the having magnitude 20 kilonewton per meter. So 80 kilonewton meter is we have done it correctly, right? Yeah, 80 kilonewton meter will be the maximum bending moment at D, point D max. This will be 80 kilonewton meter. Now, let us do this question. This question here, they are trying to tell a wheel load of 20 kilonewton is moving on the following beam from left to right. Left to right means like this. 20 kilonewton is moving. 20 kilonewton means only one load is there. 20 kilonewton. What is the maximum shear force at point E, which is located at, this is point E, which is located 3 meter, means from here, joint D, means this will be 2 meter. Now, when you will cut, I am directly doing it. When you will cut it here and apply a shear release, you will see, you are getting the ILD for shear force at E will be something like this. This will be now this from Muller-Breslau principle we know this should be delta equal to 1. Now check, this is 3 meter, this is 2 meter, this is 2 meter. So what you can write, this is theta, this will also be theta, and this line should be same. So this you can write 3 by 5, this you can write 2 by 5. You can check it afterwards. So we got the ordinate. Now we have to put this 20 kilonewton such that we will get maximum shear force at E. So if you will put your 20 kilonewton at this point, E point, what is the maximum ordinate? This will be 3 by 5, means I am not talking about the sign, but the magnitude as a whole. Let this be minus, but this minus 3.5 is more than a 2.5, means magnitude wise. So you can write 20 kilonewton into the ordinate. This is 3 by 5. So this is 12 kilonewton. So option D. Everyone got clarity, right? Means similarly, means you can write it in the same way. You can formulate the equations. Like suppose this is x, this is y, this is theta. So theta will be height by base. So you can write y by 3 equal to x by 2. Then x plus y equal to 1. So you will get two equation. I am writing it here, but I am not solving. From these two equations, you will get x as 2 by 5 and y as 3 by 5 upon solving. And after that, just multiply this ordinate, means multiply 20 kilonewton with this ordinate, you will get the maximum shear force at the desired point for the given question. Now, check this question. If two load of 100 kilonewton and 20 kilonewton separated by 1 meter moves from left to right on the beam shown in question 7, then the maximum hogging bending moment at point E will be, or each. Means they are telling now we have two moving loads of 100 kilonewton separated by 1 meter moves from left to right, and 100 kilonewton is following, means it is lagging to 20 kilonewton. Means this is the setup. Now what they are saying, maximum bending moment we have to calculate at point E. So let us draw it here again. This is like this. This is like this. Now this is 3 meter. This is 2 meter, 2 meter, 2 meter. Now this is point E. So you have to calculate maximum hogging bending moment at point E. So what you can do, if you want to calculate maximum hogging bending moment, just add a bending release. Draw the ILD for bending moment at E. So it will be something like this. When we will give unit rotation, so it will be taking a shape like this. This is negative, this is negative, this is positive. This is 2 meter, this is 3 meter, this is 2 meter, this is 2 meter. Now, we have to place these two loads in such a way that we will get maximum hogging bending moment. Now, check. What will be this ordinate value? Tell me. Now, you can write theta 1 plus theta 2, the complete rotation. Theta 1 plus theta 2 is the complete rotation. You check. This is theta 1 plus theta 2, each 1. Why we are writing equal to 1? Because we have given unit rotation. That will be equal to 1. Now you check theta 1 will be this height. Suppose this height is x. X by 3 plus theta 2 will be x by 2. Should be equal to 1. So take LCM. This will be 5x. Will be equal to 1. X will be 6 by 5. So this ordinate is 6 by 5. Now, so this is if now theta 1 will be x by 3. So x is 6 by 5 whole divided by 3. So 6 by 15. So theta 1 is 6 by 15. Now theta 1 for this triangle you check. If this is ABC, for triangle ABC, theta 1 will be AB by BC. BC is 2 and this is 6 by 15 will be equal to AB by 2. So from here we are getting AB equal to 6 by 15 into 2. So 12 by 15. So this height is 12 by 15. Similarly, this will be theta 2 and we know theta 2 is x by 2 and x by 2 is 6 by 5 into 2 is 10 and that will be equal to this height. Suppose this is z by 2. So from here z you are getting 12 by 10. So this is 1.2. Now tell me, to get maximum hogging bending moment, you have to place the load in positive part or negative part. Tell me.
Negative parts.
Negative part. Now, this is the negative part and this part is the negative part. Now, see, this is also 2 meter negative, means zone width is 2 meter. This side is also 2 meter width. But here Z value is greater than 1. To be precise, 1.2. Here it is less than 1. So, it is better to place the load where the ordinate are maximum to get the maximum hogging bending moment. So let us place 20 kilonewton at this part and after 1 meter 100 kilonewton and check. So it is like this, 1.22. In 2 meter horizontal distance, the vertical lift is 1.2. So in 1 meter, it will be 0.6. Now, when we are placing it like this, we will get 100 and its corresponding ordinate will be 0.6 and 20 and its corresponding ordinate will be 1.2. So it is 60 plus 24, 84 kilonewton. But let us check one more case. If moves from left to right, if we are not placing 20 kilonewton anywhere between our beam and we are placing 100 kilonewton directly here, in this maximum ordinate point. So we will get 100 into 1.2.
120 kilonewton.
120. 120 kilonewton. This should be the answer. Left to right. Have we done some calculation mistake in finding out the ordinates?
We'll try with the extreme left, sir.
Extreme left, there might be more cases. Then let us take this triangle also. Ordinates are correct. Please check if this is coming out to be 12/15 or something else. Otherwise, again, our complete calculation will be wrong. When we are placing 100 kilonewton here and 20 kilonewton here, it will give, for this case, 100 into 12/15 plus 20 into 6/15. 100 into 12/15 plus 6 into 20 into 6/15. From this case, we are getting 88. From this case, we are getting 84. And from this case, 120. But options are not matching. Just check if we have calculated those ordinates correctly or not. If those ordinates will be wrong, then complete answers will be wrong. Can anyone please tell if the ordinates are correct or not?
Correct, sir.
Correct, sir. Correct. Yeah.
Then let us put in the positive side and let us check if maximum sagging bending moment is matching with any of the results or not. For this case, if we will put here 100, let us put 100 in this maximum ordinate, maximum positive ordinate. So it will be 100 into 6/5 and 20 kilonewton right side. So 20 into, in 2 meter lift is 6/5. In 1 meter lift will be 3/5. Check this value.
$132.
132 kilonewton. Might be that maximum hogging they are writing, but it should be sagging. If sagging, then 132 is correct. If hogging, then 120 will be the answer. If the ordinates are correct. I think the ordinates are correct. So maximum hogging will be 120, maximum sagging will be 130. Got it, right?
Yes, sir. Yes.
Yeah. Now come to this question. I am giving the hint and you try it yourself. Now, here, this is the not any repeat question from this class. In this question, they are asking to determine the absolute maximum bending moment due to 3 wheel loads shown below. So, for determining maximum bending moment, first you determine the resultant for this train of loads. Okay. So to determine the resultant, Let us take movement about point, suppose A or 80 kilonewton. So we can write movement about point A will be equal to 0. So we can write 100 into 3 plus 60 into 2 equal to R into this is X bar. So X bar will be equal to 100 into 3 plus 60 into 2 by total resultant will be 100 plus 60 plus 80. So it will be 140, 240 kilonewton. So 240. So what you are getting? 100 into 3 plus 60 into 2, 4.25. You are doing it correctly or not? Or not? 100 into 3 is clockwise, 60 into 2 is also clockwise, by 60 into 80, 150 to 50. This is 1.73. This is 1.75. So this X bar is 1.75 meter from this point A. Now, so you got here, this is 100 kilonewton, this is 60 kilonewton, this is 80 kilonewton, and your resultant is acting here, which is at a distance of 1.75 meter from this point A. Till this point it is clear. Now, you have between this resultant, the resultant is clubbed or is in between two forces. This is 60 kilonewton and 80 kilonewton. Now, case 1, you in between this resultant and this 80 kilonewton, the distance is 1.75 meter. So you take the midpoint, let the midpoint be C, take the midpoint at C and place this C at the mid span of this beam AB, such that these C and C prime points are coinciding. Now, you draw the ILD. Now, this will be your 1.75 by 2. This side at this point, it will be 80 kilonewton. And taking this 80 kilonewton, you draw the ILD. The ILD will come like this. Now, place all other loads. This is 60 kilonewton and this is 100 kilonewton. Now, corresponding to 100 kilonewton, you calculate this ordinate. Corresponding to 60 kilonewton, you calculate the ordinate, and corresponding to 80 kilonewton, you calculate the ordinate. Multiply it. For case 1, you will get bending moment maximum 1, some value. Second case, you take between 60 kilonewton and this resultant, this distance is 2 minus 1.75, whatever value. Take this midpoint, place it, let this be C double prime. Take this C double prime and place it over the midspan point, that is C prime. And taking this 60 kilonewton as your base point, draw the ILD such that your ILD, maximum ordinate of the ILD will be under 60 kilonewton, and you will get this y coordinate. This will be AB by L, and correspondingly you determine the ordinate of 100 kilonewton and 80 kilonewton and calculate PM max 2. Now your answer will be bending moment absolute will be maximum of these two. This is the complete thing you have to do. Now take this as assignment, means one of the question, you can try it by yourself. That's it for today's class. If any doubt, you can ask me now. That's all from my side. If you have any queries, any doubt, you just get it clarified now. No doubts? So I am closing this. Thank you.
Thank you, sir.
Thank you, sir.